All right, guys, welcome back. We are moving on into our next major topic in the CCIE Routing and Switching Mentorship Program. We're going to be talking about the Border Gateway Protocol. And if you look at what we're going to be talking about with regard to BGP, it's quite an extensive discussion. It's probably the second, outside of OSPF, it's the second longest section that we cover in this course. All right, we're going to start by doing just a basic BGP overview, kind of clear out the cobwebs if you haven't dealt with BGP in a while. And then our next lesson, we'll get into some of the BGP operations. How do we form peering relationships? We'll talk a little bit about some of the operational stuff this time. I'll talk about the protocol itself and different message types and so on, but we'll get into it in more detail again in the next lesson. And then we'll talk about some of the pairing relationship rules. We'll look at some iBGP configurations, route reflector configurations, confederations, next hop processing, network layer reachability information, best path selection, etc. I mean, there's a lot to talk about with BGP. And you definitely need to, this is, I would say, probably the most or the second most important topic of the entire program. All right, so we're going to spend a lot of time. We'll probably be repeating some of this information as well in some of the other lessons in the future. For example, we'll talk about some of the operational stuff today, and then we'll get into it again. This particular lesson, we actually don't have any configurations. That's what we're going to be seeing in the next video series. So we're going to be taking notes, and I'll be posting these notes in the Google Drive for you guys to download, and you can access this information. So in this section, we are going to kind of begin with an overview of BGP operations. What is BGP? You know, what are the use cases for BGP? And what is BGP not? Because there's a lot of misconceptions of, you know, what BGP isn't, right? Or what BGP is, but we don't necessarily understand what BGP is not. And I think you guys will be enlightened a little bit when we talk about that today with regard to the protocol itself, and it will change your consideration as to how you decide to implement BGP in your own enterprise. As compared to an IGP protocol, right? BGP is significantly different than any kind of core IGP because we have a lot of different ways that it works. All right, and we are going to be talking about that quite a bit over the next hour or so, and then on into a lot of our other discussions as well. All right, what are the use cases for IGP, right? Where would I decide to implement my IGP protocols as opposed to BGP, and so on. So as a protocol itself, BGP is an open standards based protocol. All right, number one. It is also a path vector protocol, although a lot of people will tend to classify BGP as a distance vector protocol from the perspective of autonomous system to autonomous system. That's one of the concepts that we'll see as we start to get into more details about BGP. You know, why do we tend to classify it as as path vector when it tends to act like distance vector, meaning that we don't have a complete picture of the overall topology, but we're trying to establish essentially routing through the domain. All right. It's also an exterior gateway routing protocol, and that means that we tend to use this protocol to route between autonomous systems as opposed to inside of an autonomous system. Interestingly enough, though, BGP is not even really a protocol. And that's one of the things that I wanted to show you guys today. Compared to, say, like OSPF or EIGRP, BGP is significantly different in the way it handles transport, in the way it exchanges prefix information, and so on. It is based on the original RFC, which is RFC 4271. RFC 4271 is kind of the original RFC, but there have been a lot of different addendums and to BGP as a protocol. One of the things that makes BGP so unique is its extensibility, customizability, and scalability. So there have been a lot of different RFCs that have been added beyond the original RFC. I would recommend, though, taking a look possibly at the original RFC just to kind of get an understanding. We'll actually reference it as we kind of go through a lot of our BGP discussions over the next few lessons. All right. Things like using, say, communities for traffic engineering, there was an RFC written specifically for that. The nice thing about 4271, though, is it's going to give you the foundational information, like how do I establish peering relationships, how do I define my reachability information between my peers, and so on. All right. Being that it is a path vector protocol, it means that we use attributes to make routing decisions. As a path vector routing protocol, we use prefix attributes, I should say. And that's one of the things too that's different significantly from BGP to an IGP, is that everything is based on the prefix, not on the link, to make routing decisions. There are over 13 core decisions that are made when we're deciding how to route with BGP. All right. Now, we don't usually get beyond maybe 4 or 5 or 6 different options, but the decision tree that we use in BGP is pretty complex. We're not using traditional, delays, bandwidths, reliability, those kinds of things to be able to make our path selection decisions. All right. Now, the fact that it is a path vector protocol means that it's very easy to apply policies for traffic engineering in BGP because the attributes themselves belong to the routes as opposed to the attributes belonging to the links, right? So let's say, for example, in OSPF or EIGRP, I want to influence traffic decisions, right? I would change, say, the bandwidth of an interface or the cost of an interface. I might modify the delay. I might change some K values. Different components that allow me to change how route selection is done. But inevitably, unless I'm using some very complex filtering options and policy-based routing decisions, inevitably, whatever I change at the link level is not going to just affect one route. It's going to affect a lot of different routes. But in the case of BGP, the attributes apply to the prefix on a per prefix basis and not the links themselves. All right, so that gives us the ability to use these multiple attributes to make different routing decisions based on prefix destinations. And ultimately, we're trying to influence next hop selection. We don't use BGP to facilitate routing to the next hop, but we will use BGP to identify what that next hop is going to be. So it's very easy to apply these policies for things like traffic engineering and BGP because of that behavior. All right. Exterior protocols are typically used to route traffic between autonomous systems. For example, internet-based routing. But that's not also not necessarily something that has to happen, right? The concept of routing across different through different autonomous systems, of course, applies to BGP when it comes to the internet because of the number of prefixes and the scalability of the internet. But we can use BGP for scalability purposes, and there are many other use cases where you may want to use BGP internally. All right. So clearly, from a use case perspective, I'll just put this in uppercase. We use BGP to route between external ASs on the internet, but there are other use cases, right? So, for example, you can use it for large data center designs. We'll talk a little bit more about that a little bit later on. There's actually an RFC that describes that functionality and that capability. It's a fairly new concept. We'll talk about that a little bit later on. We can use it for scaling DMVPN. Because the BGP topology is arbitrary, it gives us the ability to do things like filtering and summarization, or aggregation, I should say, in the case of BGP, at any point in the topology, so we can use it to scale DMVPNs. There's a lot of applications for BGP, all right? And in the case of scaling those DMVPNs, we might even use locally significant ASNs. ASN is an autonomous system number, all right? It is perhaps the most extensible routing protocol routing application, and it is the most scalable application out there presently. There may be some other ones that come in the future, but it's constantly getting features added to it through its extensibility, and we add functionality. The extensibility and scalability comes from the use of what we call AFIs, or what we call address family identifiers, or sub-AFIs, SAFIs. So sub-AFIs. We'll get into that a little bit more as well. Obviously, when we do our implementation, we talk about the protocol and how we implement the protocol. We're talking about much, much more than defining network layer reachability with IPv4, right? We can work with IPv6 unicast. We can work with IPv4 and IPv6 multicast, IPv4 and IPv6 MPLS, MDT, VPLS, layer 2 VPNs, all kinds of topologies, all right? It's an extremely scalable protocol, right? From a scalability perspective, currently, as of this recording today, over 800,000 v4 prefixes in the database. And in the IPv6 space, it's less. I think it's about 70,000. We'll check, actually. There's a place we can check this, but prefixes in IPv6. All right. It's just a really, really scalable protocol. In fact, let me go ahead and bring this up. I brought up a page here, and it's called BGP.pataroo.net, and it gives you an idea of how BGP has scaled over the years looking at the routing table. All right, so you can see back in 1994, we were talking about significantly less than 100,000 routes, and now we're in 2000, getting into 2019, we're close to 1 million different routes. So it's incremented significantly. And if we look at specifically the number, this is from the perspective of this node in the where they're pulling the data from. So this is Asia Pacific, the Asia Pacific Regional Internet Registry, 788,430 prefixes, and they're using that Internet Exchange router, routeviews.oregon-ix.net, as a reference. We'll actually log into that in a little bit. I'll show you guys. Let me copy this link here. So we're going to pull that up. We'll take a look at that. That's basically a reference point on the internet that allows us to check the global routing table and see how many routes exist. And you can see the V6 database is significantly smaller. It is growing, 72,482 different prefixes. That doesn't mean that that's all the choices that we have. There's actually millions and millions and millions of choices to reach those destinations, but it's a lot of different prefixes. All right. It is a very, very stable routing protocol as well. The thing about BGP, in its stability is that it does tend to be slow as a converging protocol, but that's by design, and we'll talk about that as well. All right. If you look at the CIDR database and take a look at these CIDR reports, we can actually see all of the different prefixes that are being advertised by different autonomous system numbers. All right, and we can kind of identify. This is not the report that I was looking for. Let's see. And that's not what I wanted either. I want to see the, maybe it's under IPv4. Let me check IPv4. And we should see address blocks. Yeah, so we can see the different address blocks that are allocated, and what autonomous system number they're related to, which regional internet registry they're assigned to. There's a lot of good information here, but we're going to take a look in a real router and take a look at what those prefixes look like in a real router. Okay. Now, one of the interesting things about BGP is that it depends on where you are in the physical internet, right? You may have a different view than other devices in the topology. So this is from the perspective of one router, specifically this router right here, routeviews.oregon-ix.net. That's from the perspective of that router. All right. We'll log into that router. We'll take a look. I'm going to kind of walk you through on how to read some of that information in that database. Because one of the things that you have to decide if you're going to run BGP is how you're going to sync or create BGP information in your own domain, if it is in fact information that you need. It may not be feasible or possible to incorporate every single route that exists on the internet. All right. In our lab topology, the routers are going to be making kind of different decisions, based on where they are in the topology. We'll take a look at that topology in the next lesson. How does that best path selection process work, right? That's what we need to learn. And how does BGP decide how to route two different prefixes, all right? There is a lot with BGP, specifically because of its flexibility, okay? Now, what is BGP Not? So let's take some notes here. What is BGP Not? What is BGP Not? A routing protocol. Believe it or not, it's actually not a routing protocol. It is an application designed that runs on top of TCP, designed to exchange what we call NLRI, or network layer reachability information. Essentially being able to identify that prefixes exist, okay? In most cases, BGP cannot be used by itself to route to a specific network or a specific destination. BGP is basically a reachability protocol. Well, this is not supposed to be under what is not, but is a reachability protocol. Meaning that it needs to be able to identify that prefixes exist, and it needs to know what nodes those prefixes are attached to, or at least reachable from. But then we're going to rely on some sort of underlying IGP for the route recursion and for the transport of the packets themselves. All right? We're actually going to demonstrate this concept many times as we go through some of our other discussions later on about BGP. We're going to see how BGP establishes its peerings. BGP doesn't have its own transport protocol, right? So no transport protocol. Now, what I mean to say by that is as an example, OSPF uses IP Protocol 89, and EIGRP uses IP Protocol 88. In BGP, there is no separate transport protocol to transport datagrams for BGP peers. We're actually using the underlying protocols to route that information, like EIGRP and OSPF. BGP rides on top of TCP, specifically TCP port 179. Guess I should make a note of that. Default port is port 179. All right. So there needs to be some sort of underlying IGP. So BGP can use TCP port 179 to exchange those segments, and it relies on that IGP to do the route recursion to reach different destinations. That's a very important concept. All right. All right. I guess the point I'm trying to make, guys, is that there is a clear distinction between where BGP is used, what it does at the control plane, which is basically an application to establish peering relationships, and then advertising application data. And that application data is our v4 prefixes, our v6 prefixes, multicast information, whatever we can transport in the address family scenario. All right. In general, BGP cannot be used as a routing protocol of the actual data itself. There are some, I guess, some very unique design scenarios where you might run into that. I'll wrap up today's lesson by kind of talking about that aspect. But really the key is to understand that BGP needs some sort of underlying IGP to work 99% of the time. All right. The IGP protocols, we've talked about EIGRP, we talked about RIP, we talked about OSPF. Those protocols are generally going to have visibility of the topology because they have algorithms and structures built to be able to identify what that topology is, right? The shortest path first algorithm in OSPF, dual in EIGRP, and so on, that allows us to recurse and resolve reachability between endpoints by building graphs, right? And SPF describes the graph in OSPF and how peers reach each other and so on and so forth. That's why we have such a complex linked state database in this particular case. All right. Also keep in mind, I've already mentioned this once, but IGP protocols make their routing decisions based on the link attributes, like the cost of the link and so on, not prefix-based attributes. So in the case of IGP routing, IGP policy application is much harder to do because changing how I route to, say, destination X, maybe I say I'm going to go ahead and choose path whatever. Most likely that's going to affect network Y as well. And if they're in the same location or whatever. All right. So with regard to IGP versus BGP, which is an exterior gateway protocol, not to be confused with the defunct EGP protocol. BGP has no visibility into the topology. It's routing from AS to AS. That's it. Within the AS, we rely on that IGP protocol. All right, so BGP uses the IGP as a transport to advertise reachability to the destination prefixes. BGP does not actually make the decision of how to route the traffic. All right, so basically what I'm saying is BGP is going to say, hey, I know about prefix X, and by the way, this is the next hop for prefix X, but I don't know necessarily what decision I make on the routing side to actually get to that next hop. And that's where the IGP process comes into play. I always describe essentially BGP as an overlay to an underlying IGP transport. Very much like the VPN technologies that we talked about in some of our previous lessons. All right? There has to be some sort of method to do route recursion to be able to forward our traffic. All right, BGP is only really going to know logically what's happening, who they're establishing sessions with, and so on. We'll talk about the rules, by the way, of how we establish BGP peering relationships and so on as we get into some more of the details over the next couple of lessons. All right, I mean, think about it. Here's an analogy, right? You go to your computer, you want to watch the new trailer for Top Gun, right? You go to YouTube, you pull it up. Put in an address, you pull it up, right? You don't really necessarily know the underlying network that allowed you to get to that video, but you know that it resolved and it worked, because that's essentially what the internet is. It's the same concept with BGP. I know basically about what exists, but I don't know the underlying details about how to reach that information. All right? The application data, essentially in the case of BGP though, using this analogy, is the network layer reachability information. All right? Now, one of the things that we'll spend a lot of time talking about is how BGP makes decisions based on individual vector attributes based on the prefixes. That is the opposite of IGP. Again, IGP protocols look at attributes of the link, whereas BGP looks at attributes of the prefix. All right? Very, very easy. We can change how we route to prefix X versus prefix Y. Maybe we change the local preference for X, or we do some sort of AS path prepending for Y, or whatever. You know, depending on one of those 13 decisions that we can manipulate, we will decide how to route from one prefix to the next. Now that means that we have the ability then to implement either a granular policy globally across the entire platform, or even through an AS, or on a per peer basis. So we can manipulate how traffic enters or leaves our network based on our peering relationships. The policy application is easy because there's a way that we can change this on a per prefix basis. And that's what gives us all of the flexibility that we need to be able to control BGP. Now, a big part of our future discussions are going to be, what are those attributes? How can I change those attributes? How can I use them? How do I interpret them? What are the ways that we can actually influence how traffic flows through a BGP system? Okay? So what is the primary use of BGP? Well, the main reason is policy application. Just because you're connected to multiple providers doesn't mean you have to use BGP. It really depends on what your overall needs are. All right, we'll actually take a look at some of those scenarios as well. Like, when do I decide to use BGP, when do I not? Right? You only need to really implement BGP if you have some sort of diverse connectivity between multiple peers and you want to implement some sort of policy routing based on those diverse connections. All right? So we're going to see that when we do the policy application, it's really easy to manipulate the traffic flow as long as you have a good, solid understanding of what those attributes are. What is a well-known mandatory attribute? What is a non-discretionary attribute? What is a transitive versus non-transitive attribute, and so on. We'll talk about all those concepts over the next few lessons. Okay? Now, it's pretty easy in BGP to manipulate how traffic leaves the network or egresses your network. Now, there are a couple of mechanisms that allow us to influence how traffic comes into our autonomous system as well, but ultimately the originator of the traffic is going to have the final say as to how the traffic is going to be controlled. So I'm always going to have control over how my traffic leaves my network. I can try to influence peers on how traffic should return back to my network, but I don't necessarily have ultimate control over that. Okay? There are many different ways we can attempt to do this. We can maybe do AS path prepending. We could use the MED or multi-exit discriminator attribute. We can do signaling with BGP communities, etc. All these things, which are terms you're probably not familiar with, are things that we will be discussing and going through over our next few lessons. And we're actually going to be manipulating these values using route maps and all kinds of ways to manipulate the traffic. Now, if I'm just peering with a couple of different ASs, it's pretty simple. On the internet scale, it's a lot more difficult, and so on. All right, so when do I use BGP versus when do I not use BGP? Well, we have essentially two classifications of prefixes in with regard to our BGP discussion. Prefix designations. We have one that's called a provider. I lost my train of thought there. I know one of them. I'm trying to think of the other one now. PA versus IP, or PI. Provider independent versus provider. What the heck is the PA? I'm missing it now. All right, we've got provider assigned addresses. That was the term I was looking for when I was trying to spit it out there. Provider assigned addresses, what we call PA addressing. And what's unique about this addressing, obviously, is the ISP or TSP owns your address space. And this is pretty typical for a lot of businesses. So they define the policy. And we're seeing more and more that organizations want to have provider independent address space as opposed to provider assigned address space. In this case, BGP is most likely not needed because you're not the one making the policy decisions. You're simply routing, statically to the internet or whatever. Okay, and then we have the provider independent addressing. I'll just make it consistent here. Obviously, in this case, you own your address space, meaning that you got prefixes assigned to you most likely by your regional internet registry. It's unlikely you got it assigned directly by the IANA, but I think maybe in some cases that could happen, but probably not actually. I think you always have to deal with the regional internet registries. You dictate the policy because you own the addresses. It's not easy though, right? In this case, BGP is most likely needed. All right, and it's a lot of work. And I make a kind of a joke about that, but you have to apply for public BGP ASN. You have to justify the need to have your own provider independent address space and so on. So it's not an easy thing to accomplish. All right. Most of your tier 1 and tier 2 providers, they're going to be using BGP to construct the internet. They're going to have peering agreements and so on. What are some of the other considerations, though, that I have with BGP? Right? So if I decide that I do need to run BGP, do I need to get the entire 800,000 prefix database? Right? Do I have to have full resolvability? In a lot of cases, that's not the case, right? You may want to be able to get a subset of those prefixes for the providers that you're connected to, maybe the prefixes that they own, so you can leak out those routes and make independent routing decisions on how to reach those particular destinations, right? But the other thing to consider is, does the RIB have enough memory in your platform, right? The routing information base. Can the forwarding information base actually be installed on the line card, right? Can the router even take the entire view? Just because you have a lot of memory doesn't mean you can install all those routes in the forwarding table. So let's take a look at that route server that I mentioned before. Take a look at what the current topology looks like This will be our only kind of lab, if you will, for this particular scenario. Right? So this is a BGP Organ Exchange BGP route viewer. We can't influence internet routing through this router, but we can look at things like show IP BGP or show IP BGP summary. And again, this is from the perspective of a router on the West Coast. You guys can connect to this guy as well. So if I do a show IP BGP summary, I can see from this output here, might take a minute to run. These routers are heavily taxed, but I can see from this output here 800,516 different network entries using this much memory. Now, that might not look like a whole lot of memory compared to, say, like a standard computing resource, but when you compare this to the amount of memory that a traditional, ISR router or like a 4400 series router might have and so on, it's significantly different. All right. Now, not only do we have memory allocated for the number of network entries, but look at the number of path entries that we have. What is that? Let's see, 23,724,142 different path entries. Meaning that even though we only have 800,000 prefixes, we have 20-something million ways of getting to those prefixes. And of course, that's part of the whole calculation, right? BGP is going to have to figure out, make a decision based on those paths, how to reach a particular destination. Okay? But we also have other things, memory allocated for things like deciding what the best path is, AS path information, attributes, communities, extended community entries, and so on. So every one of these functions within BGP requires a specific amount of memory. Look at this one here. That's the most significant, right? We have, looks like 3.6 million best paths. 36217, nope, yeah. Let's see, 1, 2, 3, 4, 5, yeah, 3.62 million best paths. And then these are the attributes that are tied to those best paths. All right, now you could sit here and hit the space bar and you would see a list of prefixes. And we'll actually talk about how to read this database and what all these numbers mean. What is the AS? What is the state prefix received from that particular peer? And we'll actually talk about the attributes as well. If I do a show IP BGP, this actually will show me the BGP database, and I can start to see for this 1.0.0.0 network, these are all the next hops options that I have to reach that particular destination. Now, this happens to be the one that's being used by this particular router to reach 202.232.0. To reach 1.0.0.0/24. All right. So if I did a trace route, I don't know if it'll let me do that, but trace route to 1.0.0.1, I should see it pretty much taking that path. 202, it's going to be in there somewhere. We're not quite seeing it. I like that. 1.1.1.1. That's the actual domain name. It's crazy. All right. But anyway, we'll get into this later on. We're going to talk about what is the metric value, what is local preference, what is weight, what is the AS path, what's the origin code. We'll talk about all of these different attributes later on and how we interpret this database, how we read it, and so on. All right. So once I go to advertise my prefixes out, let's say I'm originating my own prefixes and I want to advertise those prefixes out. There's no way, and I've applied some sort of policy application to those prefixes, there's no way I can see that policy applied locally on my router. So I have to go to other neighbors to see how the route servers see what their view is when they route traffic back to me. So we can use these route servers, and there's thousands and thousands of them all over the place. right, to make policy decision. Okay? All the traffic in the internet most likely will route to some sort of tier 1 provider at some point, but we have tier 2, tier 3, and so on. All right? So we have attributes in the path. We have different views for all these different peers and how I'm going to make my routing decision. The selection process I'm going to use is what we have to determine. All right. Now, once I've determined that, I'm going to download that information from the BGP rib to the global rib, which is my global routing table. And then most likely that's going to end up getting installed in the forwarding information base or the CEF table. Right? So if CEF is implemented in hardware, I have to consider, can the router handle this amount of information? All right, so if I do a couple of tests here, let's see if we can figure something out. So if I do a ping google.com, all right, oh, it resolved to IPv6. Let's try ping IP. All right, so we got address of 172.217.14.1, excuse me, 172.217.11.174. So if I do a show IP BGP 172.217.11.174, I can see that there's 31 available ways to reach that destination, and I've opted to use number 27. Okay? So if we kind of scroll through this, there's 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and finally 27. Okay? So essentially what we're looking at here, my longest match to reach that particular destination, that's all the way back at the top. I'll show you that, but it was a /24 in our particular case. And we see the 1351 space 15169. Well, these are the autonomous system numbers that I go through to reach that destination. So this is the ASN that I'm peered with, that this route server is peered with, 1351. And I can actually see who owns that autonomous system number. 1351 is the University of Vermont. And most likely the other one is probably going to be Google, because that's where I'm going. So 15169, let's go back to our page. That's probably going to be Google. Yeah, Google Inc. All right. Registered to ARIN, which is the Regional Internet Registry for North America. All right. But we're seeing all kinds of things here. So we're going through 1351, then 151.69. That would be considered the AS path attribute. But we're also seeing some other pieces to this, right? What is the origin? It was learned through some sort of IGP process. What is the local preference? Is the route valid or not? Is it external? And so on. There's some other attributes that are tied to this we don't see listed here. All right. So basically how we read this is that this Oregon IX is peering with someone who owns 1351, and then 1351 is peering with 151.69, and they're the ones that are actually addressing or advertising that address space. All right. So the right number is the originating AS, and then we prepend the other autonomous systems that we have to go through to reach that AS to that particular path. So somehow, based on all of the attributes, which we're obviously going to go into in a lot more detail in some of our future lessons, the router says, hey, look at these values. Could be MED, could be local preference. Is it eBGP or versus iBGP? What is the best path? We had 31 different choices for this route alone, keep in mind, this is happening for all 800,000 routes. That's why we have millions of choices. So this is a very, very control plane intensive protocol. If we want to take full view of the table, it's going to require a lot of control plane resources. All right. Also, keep in mind that egress and ingress policies, how I control traffic leaving my autonomous system, as opposed to how I allow traffic to enter my autonomous system, they're not related to one another. All right. You might say, for example, I'm going to use a default route out. That doesn't mean that I still can't influence how traffic comes back in. So that's one of the things that we'll take a look at, is how do we manipulate specific attributes to influence how traffic leaves and how traffic comes back into the network. You always will have ultimate control for how traffic leaves the network. You can certainly ask your peers, give them maybe some sort of preference for how you want traffic to enter the network, but it doesn't work 100% of the time. Those are what we call optional attributes. All right, in some cases they're non-transitive optional attributes, which means that the party that you're peering with may understand what the attributes are, but they're not required to facilitate them. All right, here's the thing though. Who knows if you're going to get a question on the exam that says influence path selection with traffic engineering principles in BGP, but don't use XYZ. And XYZ happen to be the simplest ways to manipulate traffic patterns. All right. Now, one of the things that I'm going to suggest that you guys read before we get into our next lesson is go out to Google and search for BGP path selection process. All right. There is a Cisco document called the BGP best path selection algorithm. It's fairly new, relatively, but it talks about all of the different values, right? So weight, and it gives you a clickable link to describe how weight works. What is the weight attribute, and so on. And then the second is local preference. And then the third is it locally originated? Do I have a network statement, or is there some sort of aggregate command in my BGP configuration? Then I'm going to prefer the shortest AS path, and so on. Like I said, we'll talk about all of these different attributes as we kind of go through the process. You can see there's 13 different choices. Some of these choices have kind of what we would refer to as sub-choices as well, based on certain criteria. Okay. What are some of the other use cases for BGP? Scaling the enterprise, right? Maybe OSPF or EIGRP has become too large, and we need to kind of break up those domains. We can use BGP in the core of the network and have these little islands of IGP. Because BGP does have an arbitrary hierarchy, it works very well in a lot of different environments. We can use it to scale DMVPN, where we set up our hubs as BGP route reflectors. And because there is no strict hierarchy, we can summarize and apply filters wherever we want. We can also apply any kind of attribute manipulation at any point in the network as well. Granted, some attributes only have effect at certain points in the topology, but we'll learn what that's all about later on as well. Okay? It makes policy application extremely easy. You could use this, for example, to scale your data center fabric. If you have a large data center design, Cisco has ACI and Nexus 9Ks. They actually make use of this particular design. So instead of using some sort of IGP protocol as your routing protocol, use BGP for routing in the cages in your data center, and then use IGPs on the external leafs, right? There's actually an RFC. Let me see if I can find it here real quick. I believe it's called BGP for routing. There it is, in large-scale data centers. RFC 7938. This document describes essentially how to use BGP to replace things like Trill or fabric path and stuff like that. We can, yeah, it's layer 3, right? We still have to route, but we could use methodologies like VXLAN or GRE for tunneling to provide our layer 2 connectivity. All right. So that's kind of the introduction to BGP. I know it wasn't a very long lesson today, but it's, you know, you have some homework, right? Make sure you read that. Probably the most important thing would be to familiarize yourself with this document here, because we're going to spend a lot of time talking about these components here, right? The best path selection algorithm within BGP. So in our next lesson, we'll get into an actual detailed discussion of the protocol itself. What are the different message types in BGP? How do we form adjacencies? How do we verify adjacencies? And so on. How do we work with the TCP keep alives? How do we work with TCP in general? Because that's kind of unique to BGP. I mean, RIP is the only other closest protocol that utilizes transport layer protocols like UDP. Couple other things, recommended things to read. I'll put that in the notes here. Additional reading. Well, this is a must. And let me go back and get the title of that. If you just search on Google for BGP best selection algorithm, you'll see it on there. There's some other stuff though. You can read the Internet for Internet Routing Architectures book. I think I had recommended this originally when we started this class. Routing, these are older books, but I mean, the protocol hasn't changed much, at least fundamentally anyway. Because TCP/IP Volume 1 doesn't include BGP, so you want to make sure you get Volume 2. Practical BGP, as if that's possible. Optimal routing design, that was the other one. Okay, now this is not your homework. I would suggest, let me do it this way to make it consistent. BGP path selection algorithm, cisco.com, must read. Even if you don't fully understand all of the components, you know, in the document, because it's a lot of clickable, kind of click here and then all of a sudden you got to click here again and click here again, and now you're 3 or 4 pages deep into you know what, a seemingly endless pile of information. But even if you just do a high-level overview or high-level pass, that will help you tremendously in our future lessons when we talk about BGP. Okay. All right, guys, we're going to wrap this lesson up for tonight. We're going to have another lesson this weekend, most likely Saturday, tomorrow, day after tomorrow. But I'll reach out to you guys on Slack. We'll get something scheduled, and we'll see you guys in the next lesson.